Okay, perfect. Thank you. Thank you very much, and good afternoon, everybody. Thanks for joining me. As Hoda mentioned, my name is Kelterborn, and I'm the education manager for the Canadian Wood Council. I figured I'd share my video for just a bit, so you can kind of put a face to a name. I think that's always helpful. I'll probably turn my webcam off shortly, just to lower bandwidth and improve audio quality. But anyway, I figured I'd talk to you guys today about kind of exciting things happening in the world of wood design and construction, and talk about some trends in the construction industry as a whole, and showcase some kind of exciting projects that are taking place around the world and here in Canada. So if you have any questions or any comments as we go, just please feel free to ask them, and if I see them in the chat, I'll try and address them as we go. But for those that aren't familiar, the Canadian Wood Council is a not-for-profit organization that basically represents the Canadian wood industry. And our mission is to maximize market access and increase demand for Canadian wood products. We do that through excellence in codes. So we work on building codes and part building code committees, both nationally and provincially, as well as develop standards, CSA 086, the wood building standard, and education. So we're basically an association of associations, and we're funded that way. A bit about myself. I started my career as a structural engineer, working in Toronto at a firm called Blackwell, and I designed a lot of mostly high-end residential projects and some commercial projects. On the screen here is a snapshot of a few of the nicer projects that I designed as an engineer. The one on the right and the bottom there were designed by well-known architects from the U.S. called Boland, Zawinski, Jackson. And they done a lot of really great work. They designed Bill Gates' house in Washington State, and a number of Apple stores across the world. So it was pretty exciting getting to work with them. Not all the projects I've worked on were this nice, but a consistent element throughout was that they were mostly built with wood. Light wood frame construction, some steel elements, some concrete, and often had quite complex structural systems to achieve the architectural intent. I also had the privilege of living and working in China for a number of years. When I first arrived in China, I worked for an agency of the BC government that had built an office in Shanghai. You can see that on the left side of the screen there. So basically, we were promoting the use of wood in China and encouraging Chinese to buy Canadian lumber. So that was pretty exciting. Today, China has many examples of both kind of leading edge mass timber projects, like Qingdao Pearl Visitor Center, which I'll talk about at the end of my talk, and very kind of basic construction in the form of bamboo scaffolding. You can see on the right side there, just a bamboo lashed together with wire. It's simple but effective. Also, while I worked in China, I was employed by a Finnish company that produced engineered wood products in Finland and sold them all over the world. So they produced glulam and plywood and LVL and sawn lumber. And they're quite a large manufacturer. And while I was there, I was able to become, while I worked for them, I became quite familiar with how they constructed with wood in Northern Europe. So I've been fortunate to have seen wood construction in different parts of the world. So for my presentation today, I thought I would start talking about the current trends in the construction market overall, then talk about some projects in Europe that demonstrate kind of industrialized construction processes, and then I'll talk about some projects in Canada. I think it's always good to remind ourselves why we should build with wood. And first and foremost, because it's renewable and completely sustainable building material. I always say wood literally grows on trees. It's remarkable that a sapling just needs some sunlight and water, nutrients, a few nutrients from the soil. And as it grows, it will remove carbon dioxide from the atmosphere, give us oxygen to breathe. And in 80 years or so, we can harvest it like any other crop and use it as a building material. And so it's really an ideal product. And also, there's been a lot of research done of the health benefits of kind of living and being in wood buildings when there's exposed wood, when you can touch and smell and see the wood. There's kind of a natural connection to it, and in educational facilities, it's proven that there's better attention and focus for students, as well as creativity. And in healthcare facilities, it's shown patients have lower stress levels because they have lower blood pressure and lower heart rates, and that leads to quicker recovery times and reduced pain perception. And it's all just by using wood to build these environments. So it's a pretty incredible building. Historically, we built with wood because it was readily available. It was easy to work with, lightweight, so we could get it from the forest to the mill to the job site. And we started building with sticks, basically dimensional lumber, so 2x4s, 2x6s, and we used planks to sheath the walls and the floors and the roofs. And that worked reasonably well, and it's still in use today, but it's labor intensive because it's kind of piece by piece. Things advanced a little further from just sticks to panels, wood-based panel products like OSB or the oriented strand board and plywood. And this enabled more complex structural systems like shear walls and floor diaphragms, and combined with engineered wood products, has enabled increasingly larger and taller wood structures, and as well as increased their performance. And now we've advanced even further with mass timber elements. So these are things like glulam, where dimensional lumber is glued together in a number of layers to create kind of homogeneous member, and cross-laminated timber, which is kind of a buzzword these days, which is kind of dimensional lumber and alternating layers that create these large panels. Similarly, dowel laminated timber and nail laminated timber are similar, and then they can create kind of these large panel elements. And so this is great because they can act like large plates, and in some instances can have two-way capacity if required. Highly processed products where the naturally occurring defects in wood, like checks and splits and knots, they can be controlled and removed. And the quality of the finished product can really be assured. These can also come in the form of large elements that are made in a factory to very tight tolerances, and they can have holes to accept connections, like you see on the right side there, and also have holes and routing for MEP to be installed on site, so you don't have to do that kind of ad hoc on site. And these elements can be craned into place. Shipped to the job site and craned into place immediately, and suddenly you can erect the floor of an office building in 1 week. No form work is required. You don't have to tie rebar. There's not 100 concrete trucks disturbing the neighborhood. You don't have to wait weeks to strip the formwork and then reshore. So mass timber can really represent a new kind of construction. And this is hugely important as productivity in the construction industry is notoriously horrendous. So this is a chart of productivity for most major U.S. industries starting in 1947. So basically just after the Second World War. You can see productivity, basically the ratio of how much you put in versus, the ratio of how much you get out versus how much effort was put in, has exploded in most industries over the past 70 years. So the blue line at the top there is agriculture. So it's productivity in agriculture has improved 16 times in 70 years. So you can imagine a farm in the late 40s looks vastly different than a farm of today. They've used leverage scale through land assembly and automation, advanced bioengineering to increase crop yields. Similarly, automotive manufacturing has improved almost 9 times. They've implemented new concepts of flow and standardized designs, and really aggressively automated to increase production capacity. So, an assembly line in the 40s, there were a lot of people, and it was quite slow. Whereas today, there's robots everywhere, and it's quite a fast, efficient process. Likewise, retail has improved about 8 times in productivity. Walmart today is vastly different than 1940s Walmart. We think of cutting-edge logistics to provide affordable goods to the masses, online shopping, and other changes. Meanwhile, construction is the orange line at the very bottom, has improved only 10% in the past 70 years. And most of that advancement was between 1947 and 1970, likely because of the introduction of power tools and equipment to the job site. So think like electric drills and pneumatic nail guns and things of that nature. And since 1970, it's declined even further. It's actually declined productivity. So it's almost embarrassing. And this chart actually only goes up till 2010, which is around the time the iPhone was introduced. So I can only imagine that the productivity on construction sites has decreased even further since then. In the picture at the top right of the screen there is from 1833. Very similar to a lot of single-family homes in a subdivision being framed today. A loose pile of material is dropped on the site, and a bunch of people go about constructing the building one piece at a time. So, not a lot has changed over 100 years. And for context, we can consider the Empire State Building, the design, planning, and construction of which took just 20 months from preliminary design to occupancy, and the actual structure itself was erected in only 410 days. Using a crew of about 3,400 people each day, they assembled its skeleton at a record pace of about 4.5 stories per week. Using kind of an assembly line process, and the project was finished ahead of time and under budget, which is pretty rare these days. And they came with a human toll. They estimated about 5 people lost their lives during construction. So we've come a long way with regards to worker safety, but the efficiency of construction hasn't really improved because to build a skyscraper of this size today would take way longer than 410 days. And it's important to remember kind of how inefficient construction is when we consider the size of the market. Globally this year, the construction industry will be worth about $10.3 trillion, about 4 times the amount of the auto industry and the telecom industry combined. So it's a huge market, and there's a lot of money to be made, and not a lot has changed in well over 100 years to make it more efficient and make it better. And really that means there's huge economic opportunity, especially if you can figure out a way to build faster and a way to build smarter, really more efficient. And so what's really interesting is that we're seeing now tech companies taking notice of this vacuum of advancement in the construction sector, and they see construction as a market that is really ready for disruption, because in the tech industry things are constantly changing and evolving almost overnight. We get a new iPhone every year, and things are constantly improving, and the tech industry can't believe the construction industry is doing things the same way they did 100 years ago. So now, big companies like Alphabet, who have a lot of money and capacity and influence, are getting involved because they see a huge economic opportunity. And what's further interesting is they often recognize wood as the backbone of the platform in changing the construction industry, and not just because of its environmental benefits, but because wood lends itself very well to more efficient, industrialized construction. And so we're seeing startup companies like Katerra, which is based in Silicon Valley, and whose CEO used to run Tesla for a bit. And Katerra wants to change construction through technology. The construction industry is actually the least digitized, or one of the least digitized major industries. And so it's, there's a correlation there between digitization and productivity. And so they want to change that and bring technology in and kind of invert the process. So the status quo is kind of, there's a few designers at the beginning stages and designing everything, and then the builders are in a separate room, and nobody really knows what each other's doing. And then at the tail end of the project, there's a lot of people on site trying to figure everything out, and there's a lot of waste and redundancy and errors. Katerra wants to inverse that, so a lot of time is spent at the beginning, basically developing a kit of parts and completely vertically integrated, so that they control every product and every process. And basically, there's a lot of effort at the beginning, and then at the tail end, everything's assembled on site like a kit of parts, using a lot less effort. And again, Katerra is using wood as the backbone of their system in many of their building typologies. And they just completed and commissioned the largest CLT factory in North America that they built in Washington State. So it's quite exciting to see this kind of new players coming to the market and really shaking things up, and that they recognize wood as an important catalyst in this change. And so we see on the horizon kind of a paradigm shift in construction from its current state to a more industrialized process, incorporating the concept of design for manufacture and assembly, which is an approach that focuses on the ease of manufacture and the efficiency of assembly, which is most commonly used and basically it's a systems approach where the structure from the very beginning with the intention of being prefabricated offsite and then assembled on site like a kit of. So you think kind of like flat furniture, but what lends itself well. That video you just saw was a Hotel Jakarta, and it's a good example of kind of modular wood construction. And it's a 9-story luxury hotel that in just 2 weeks using 176 CLT modules. So anyway, I think it's imperative that future architects and engineers, technologists, and builders have knowledge in wood, because construction is changing, and also because we need to build a lot of new infrastructure. Globally, it's predicted by the World Bank program of the UN that we'll need housing for about 3 billion people in the next 10 years. And that's the equivalent of about 300 million new housing units that we'll require. And to meet this demand, McKinsey & Co., which is a global consultancy, estimates that about 15 to 20% of all construction in US and Europe will need to shift to modular or offsite processes by 2030 in order to meet that demand. So this is a huge potential opportunity for wood, given its desirable characteristics in these types of applications. So anyway, to illustrate how this shift to industrialization could happen, I'll kind of show you a snapshot of the current state of wood construction in Europe, and kind of talk about how they use wood, specifically in Northern Europe, where a lot of prefabrication and offsite construction technologies are already being employed and being kind of developed further each day. And so there's regional differences in Europe, obviously. So in Southern Europe, Italy, Switzerland, Austria, Germany, they tend to use CLT a bit more in their wood construction, and it's more commonly produced there. Whereas in Northern Europe, they tend to produce more LVL or laminated veneer lumber. And globally, there's about 4 times the amount of LVL produced every year than CLT. So it's quite a more widely available material. And there's basically 2 types of LVL. So there's the standard type, or LVLS, which is commonly used for beams or joists or columns, and all the plies. So LVL is made up of these small plies that are glued together, and so all the plies are in the same direction. The other type of LVL is LVLQ, it's a cross-bonded LVL, and 20% of the veneers are perpendicular. So it kind of creates a 2-way capacity, and this product's commonly used for panels, for shear walls, or plate kind of applications. So this is a video of the production of LVL, so an LVL mill. So it starts with logs that are peeled. So they take 2.5-meter logs and then they peel them with a lathe, and they create this 3-millimeter thick veneer. They kind of unwrap the log. And then they dry it to a very low moisture content. So the wood shrinks because as it loses moisture, it shrinks in dimension. And they're able to grade each veneer. So they look at where the knots are and the checks are, and they can remove those defects if needed. And then it goes into a layout process here. So they add glue, so it's a phenolic resin. And they add glue to each sheet, and then they kind of lay it up in a continuous assembly. So once all the layers are added, they put it into a press and add heat, and that allows the glue to cure, and then you have this really long kind of continuous billet of solid wood. It can then be cut into different widths and lengths, and packaged accordingly. So it's just a good video to see that these are really highly processed materials. It's not like a 2x4 where there's defects that can't really be controlled. This is a very highly processed product, and because of that processing, you can really control the quality. So over the past 15 years in Northern Europe, they've taken these LVL components because they're very precise and the quality can be assured, and they've began creating kind of prefabricated components, ready-made elements that are made in a factory and then shipped to a job site to be installed. So one of these prefabricated elements is called a stress skin panel, and it's completely made from LVL. It's typically used for floor and roof systems. They're very lightweight and they can achieve really long spans, especially for their weight. And again, they're made in a factory, very exact dimensions, very tight tolerances. So there's very little waste and few errors on site because they can control the quality and control the product. So there's kind of 3 different typical configurations for stress skin panels. The first is a rib slab. So they all consist of a LVLQ or cross-bonded LVL top panel that's structurally glued to standard LVL webs. And that's typically used for kind of non-insulated roof structures. The second is a box slab, which is similar, just it can be insulated easily in a factory. The third is an open block slab, which is commonly used for floors. And you can see there the kind of cross section resembles a steel I-beam, and so we know, we all know that they make steel I-beams for a reason, and that's because it's a very structurally efficient use of material. They try and get as much material away from the center of the section as possible. So a solid square rectangular section isn't very efficient, but if you can push that material and that mass away from the spheroid, it really helps in creating stronger and stiffer elements. Same kind of principle. This is just kind of just shows kind of how lightweight and how efficient stress skin panels can be. So this would be a comparison of a floor system spanning about 8 meters for an office floor. So an open box stress skin panel would be just over 500 millimeters deep and weigh just 58 kilograms per square meter. So very lightweight compared to CLT, which is great for many applications, but for long span floors, it's not great because again, it's a square section, so it's not a good use of material, and it can get quite thick. So CLT to do the same span would be about 3 times the amount of material and 3 times the weight. Cast in place concrete, although it would be thin, would be very heavy. It's over 6 times the weight per square meter. So you can see here just how effective this type of system is. They're very easy to build in a factory environment too. Not a lot of overhead or capital investment is required. Simple handheld power tools will do, and it usually takes about 30 minutes per square meter to assemble the panels. And again, everything is very accurate, and comes within 3 or 4 millimeters of tolerance. This is a video of a company based in Belgium that has kind of a semi-automated assembly line for stress skin panels, and they typically use them for kind of low-rise commercial applications, so warehouses and factories, and that kind of nature. So you can see that they're applying glue there, polyurethane glue. Then they use a vacuum lift to install the top panel. And then they nail it down. The nails provide a clamping force until glue dries, and then after that, the glue is doing all the work. The nails are not needed for any structural means. They install devices to allow the panels to be lifted. You can see they're quite large. That one's 20 meters long. It's probably about 2.5 meters in width. And again, lightweight. Sorry, are we having trouble hearing me? I hope everyone can hear.
Reed, after you actually turned off your video, it's okay.
Yeah.
I guess it's okay for most of the students. I guess Mario has some specific problems, so I guess we are good actually.
We're good because I could use a microphone if it's too bad, but I don't know.
That might be Mario's internet connection problem, because the rest of the class can hear you.
I can hear perfectly. I can hear. Okay. Do you want me to try a microphone or just keep going how I'm going now?
I think we can keep going because I guess it's the one system problem. Thank you.
Okay. Okay, perfect. Sorry. So anyway, these panels are put on a truck and taken to the job site. And if you speak Flemish, you can follow along with what he's saying. They're easy to join together just with screws. And again, it's a very easy and efficient assembly on site. So that's really the major benefit is again, this kind of systems approach or a kit of parts, where you try and take as much work off the job site as possible, and you do it in a factory. I've heard it been said before, you wouldn't build a car in your driveway, so why not build a car or why not build a building in a factory? It just makes sense. Another application, this is a warehouse and logistics center in Finland, just outside Helsinki. It's a company called DB Schenker, which is like a DHL or a FedEx type company. And so it's a 12,000 square meter facility, which I guess 120,000 square foot. So pretty large facility. Glulam post and beam structure with a stress skin panel roof system. And so the grid on this building is quite large. It's 18 meters that the stress skin panel spans, and then a 15-meter glulam beam span. So it's quite large considering there's pretty heavy snow load, and outside Helsinki, probably 50 to 60 pounds a square foot. So pretty good grid spacing. And really, this type of structure was selected by the general contractor for the speed of construction. So the whole wood structure was erected in just 10 weeks and completely waterproofed. So it was a very fast assembly. And the quicker you can get the building up, the quicker it can be occupied and to go into service. So it saves time and money for everybody. There's no, being that it's a logistics center, they didn't want any cross bracing or interior shear walls, so all the columns are moment connected or fixed connected at the base. So they're really large, and it creates kind of a portal frame, so they didn't need any cross bracing. So it's just an interesting application. And you can see kind of on the top right there, there's a kind of a cross or a cut through section of the stress skin panels, and so this was an open box type section, and they install the insulation in the factory as well as the waterproofing. So when the panels come to site, you basically have the building enclosure in place and ready to go. In northern Europe, they use this type of construction in a lot of shopping centers and DIY centers, like your Home Depots and that kind of thing. This particular one, you can see the panels arriving on the truck. So those are probably 25-meter long panels. So quite long spans. So the next step in industrialized wood construction is to basically increase the level of off-site construction. So this includes not just making kind of prefabricated elements that can be shipped and installed on site, but basically completely finished modules made in the factory and finished in the factory, so that basically no other work is needed on site. There's a company called Cisco, again based in Finland, that is doing this kind of work. And they're basically building apartment buildings using this kind of modular process. And so there's a video of this process. So they basically take the different elements, pre-made wall elements that you can see here. Again, this is all LVL components, which they typically tend to use LVL or other engineered wood products just because of how precise they are in terms of dimensional tolerance. Sawn lumber can sometimes have a lot of differences in dimension, and not everyone's the same. So using engineered wood products kind of ensures the quality. So here you can see the wall panels being made, and it's quite deep wall assembly, so they can fill it with insulation. It's very high thermal values. And they create the floor elements, which are stress skin panels. So this is kind of a more manual process. They don't have the automated line. I can see applying the glue to glue the elements together. And again, installing the top panel and nailing it down just to provide a clamping force for the glue to dry. I see Theodore, right? Canada does have a lot of catching up to do. So this is the bathroom kitchen pod. So it's all made of LVL. All the mechanical, electrical, plumbing is plug and play. So it's all done in the factory. You can see here the waterproofing and tiling being installed in the bathroom. So there's the finished kitchen bathroom pod. All the fixtures installed. Basically now they take these ready-made elements and put them all together in the factory. So they've just installed the bathroom pod there. And now they're installing all the gypsum board, all the cabinetry, the appliances. It's all done in the factory. And they seal it up and put it up. It takes a nice drive through the finished countryside here. So it arrives on site and the concrete foundations have already been installed. They just lift it off the truck right into place, connect the modules together. Basically takes 1 day. It takes 6 days in the factory to build each module, completely finished, and then basically 1 day on site to install them, connect all the services together. So it's very fast, very efficient. Basically it's occupied 1 month from the day that the modules arrived on site. So it's a very, very efficient way to build housing and comparably quite affordable as well. So moving on, this is kind of a different type of different typology altogether. This is more of a specialized one-off project. This is the Metropol Parasol in Seville, Spain. It's one of the world's largest wood structures, and it's created by 3,400 interconnected LVL elements. And it was completed in 2011. The structure itself, it's about 75 meters long, 50 meters wide, and about 30 meters high. And it kind of covers a huge public space. So it's not just a sculpture. You can it can be occupied. You can go up on top of it, and there's bars and restaurants, and kind of this meandering path along the top that tourists and others can kind of go and check out. So it's a pretty neat structure. You can see here it's basically created by a grid, an orthogonal grid, 1.5 meters wide by 1.5 meters, and it's supported on 6 kind of tree-like columns. So the 2 main ones are reinforced concrete, and then the 4 others are wood. And you can see on the right side of the screen there, kind of the 2 orthogonal directions. So of the 3,400 pieces used to create the structure, no 2 are alike. So they're all unique and kind of have this interesting curvature. So it was, it would be very difficult to make these shapes using any other material. And so basically they used a cross-bonded LVL product. So they took rectangular billets and then CNC'd them with a robot, a KUKA robot, and you can see there on the top left, you can get a bunch of different pieces from one rectangular billet, and then you can see, for context, there's a worker operating a crane, and comparably to the piece, it's quite it's quite large. So these aren't small pieces. One of the really neat features of this is how they connected all the different components, because the 3,400 different pieces were all kind of intersecting each other. So they created this unique kind of moment connection. So it was achieved by by drilling holes into the ends of the LVL about 2.5 feet deep, and then they'd epoxy in steel rods. And it's a very strong connection. So if you were to try and pull out those steel rods, the steel would yield and break before the connection to the wood would fail. So it's a super strong connection type. And again, being embedded in the wood protects the steel from fire. So if there was, in the event of a fire, the wood would char and protect the steel. So because when steel gets hot, it gets weaker. And it's obviously exposed to the elements, so to protect the wood from UV and rain, they coated it in a polyurethane finish, and basically this is going to allow the structure to last at least 50-year service life. So it's not like it's a temporary installation. Two pictures of the kind of construction sequence. So the site itself was kind of a very sensitive archaeological site. There's a lot of artifacts and very kind of special sites. So they had very specific locations where they could put the support columns. You can see the installation of the two main reinforced concrete towers there, and some steel infill for the lower levels. Craning into place the wood elements now, as you can see, just with in comparison to the workers, the elements are quite large. So you see this very beautiful kind of curvature and kind of wave shape taking place, and all the different connections. So there's many different connections. Just in context to show how big it actually is compared to kind of a city block. So it's quite a large structure. The final product. So you could imagine how hard it would be to create kind of that shape and all those different elements with material other than wood. So that's kind of a snapshot, well, a current snapshot of what's happening in Europe, and I'll kind of shift gears and focus on North American projects, mostly Canadian. And one specific kind of re-emerging trend in wood construction is mass timber office spaces. So this picture here is a project called T3 in Minneapolis, and it's a 7-story two-lamp post and beam project. I think it's one of the largest mass timber buildings in the U.S. right now. It's about 180,000 square feet, so size. And I say re-emerging trend because multi-story wood buildings aren't entirely new. Around the end of the 19th century, we built a lot of what's commonly called brick and beam buildings. So it's basically a masonry exterior construction with a heavy timber post and beam on the inside, and then that supports a mill deck, which is kind of 2x4 on edge nailed together. And so Toronto alone has over 40 such examples of these brick and beam buildings, ranging in height from 5 to 8 stories. Now, if you walk up Spadina Avenue, there's many different examples of these buildings you can see. Liberty Village also has quite a few. And not only have these buildings performed remarkably well over the past 100 years, considering they started their lives as textile factories or tractor factories. They're among the most sought after office space in the city. Not just because they're downtown locations, because people really like working and living in these spaces, being surrounded by the wood and being able to touch and smell and see these heavy timber structures. And so what's interesting is we didn't stop building these typologies, this kind of building, 5 to 8 story wood buildings until 1941, which is when the first National Building Code of Canada came into effect. And that first building code limited wood construction to 4 stories or less. And I guess we shouldn't, and that was almost completely based on the capacity of the fire service and the height of the ladder that they had. And back then we didn't understand very well how wood behaved in the event of a fire, and there wasn't fire suppression systems and alarms like we had today. But anyway, needless to say, we've come a long way since 1941, and kind of limiting wood to 4 stories or less is quite arbitrary. But what's interesting is developers have taken note that tenants looking for office space will pay huge premiums to rent these old brick and beam office spaces, and there's a finite supply of these old buildings, and so basically developers are recreating them using modern mass timber building systems. And a great example of this is 80 Atlantic Avenue in Liberty Village. It's being built to look like or feel like one of the old brick and beam buildings, but it has completely modern amenities and HVAC systems and high performance curtain wall systems. But it was just completed last year. It's a 5-story building with a glulam post and beam main structure. And the glulam, because it's a manufactured product, is very strong and stiff, and so you can get really long spans compared to sawn timbers that were used 100 years ago. So the grid spacing on this project was 25 feet by 20 feet. So the glulam beams, I believe, are spanning 25 feet. And in between the glulam beams is a product called NLT, or nail laminated timber. And so basically it's just dimensional lumber. In this case, they use 2x8s on edge, and they just nail them together. So it's very straightforward, and it just kind of mimics the old mill deck that they used in the old factories. The panels here were 8 feet wide and 40 feet long. They're made in a facility in Barrie, just north of the city. And they're pretty lightweight, can be transported to the site quite easily and then just craned into place. Here we're just looking at the beam to column connections. So they're all pre-assembled in the shop. The lamp components, you can see they're CNC to accept the steel connection, which is kind of, again, hidden from sight once the connection is completed. And again, that provides fire protection. So in the event of a fire, the wood will char and protect the steel from getting hot and failing. So the wood is actually protecting the steel here. Here you can just see the NLT panels being craned into place. You'll notice there's not a lot of workers on site. Just a crane operator and a couple people handling the panels. Again, they're lightweight, so they're quite easy to maneuver, and they're just easily connected. What I'll point out too is wood is much stronger, and it's parallel to grain compared to perpendicular to grain. So you think of it as a bundle of drinking straws. If you're holding it in your hand, you can easily crush the straws. But if you're to put pressure on it end to end, it's quite strong. You wouldn't be able to compress it. So wood kind of behaves in the same way. The idea here is you want the columns going kind of continuous end to end. So instead of the beam were to go right across the column, and then the column above would sit on top. The column above could crush the wood perpendicular to grain and cause settlement. So to avoid that, they have the columns come up and the beams frame into the side, and then they have these steel stubs that connect the columns end to end. So it's just always something to consider, that wood's an isotropic material, so it's got different properties depending on the grain direction. So here you can just see kind of an overview of the building. So the right is this kind of century-old brick and beam buildings, and this is the new modern building being built here. Unfortunately, the Ontario Building Code requires that 5- and 6-story wood construction have a non-combustible fire, so they had to have a concrete stair and elevator core here, which considerably slowed down construction. It's much quicker if it's an all wood structure. You can see the interior space is quite beautiful. And it's often kind of quite difficult to quantify the health benefits of living and working in a wood space. You know, you know, people say they're happier, healthier, and more productive. But an easy litmus test is just ask yourself, what office space would you feel happier and more productive in? And it's an easy answer. Moving on, a second reemerging trend is tall wood buildings. And this basically refers to buildings 12 stories or greater. And really one of the best examples of this in the world is Brock Commons, which is a student residence at UBC in Vancouver. It's an 18-story building. So the first 2 stories are in concrete, and the top 16 floors are in mass timber. Houses about 400 students. So the elevator cores are concrete, but the rest from that, it was built entirely of CLT and glulam. I have a bit of a time-lapse video here, so you can see the first and second floor podium out of concrete there, and then the 2 concrete elevator cores for lateral systems. So they're installing, so it's all flat slab. So the glulam's working in 2, or the CLT's working in 2 ways, supported by glulam columns. So all the products, all the wood elements are pre-made, back dimension in a factory, shipped to the site, and the crane picks them right off the truck and puts them, installs them right into place. It's very fast. You know, they're going 2 floors per week. And you can see the facade, the building enclosure was also prefabricated, so it's going up right behind the wood structure to protect it from the elements. So it's a pretty impressive process that they used here. The wood structure was completed in just 45 days with a crew of 9 people. So it was, you know, it was incredibly efficient. So and so a pretty impressive use of mass timber, and you know, it used 200 or 2,000, just over 2,200 cubic meters of wood. It's probably about 2,400 trees, and inevitably, you know, when we talk about we should build more with wood, it leads to the question: well, if we build more out of wood, then aren't we going to kind of lose trees and lead to deforestation? And well, the answer is no, because wood for that building was grown in our forests in just 6 minutes. So you know, we're not going to run out of trees anytime soon. And actually, you know, wood harvesting in Canada is quite sustainable. There's a lot of regulations that govern it, and strong laws and oversight. So any land, public land that's harvested has to be replanted and regenerated. Canada actually has quite a lot of forests, 347 million hectares of forests in Canada. Less than 0.5% of that is harvested annually. Actually, we lose quite a lot more forests to insect attack and forest fires. So, you know, almost 5.5% of our forests are lost each year to those 2 things, where less than 0.5% are used for harvesting for wood products. But 53 meters is quite high, and is an impressive example of wood construction, and a very successful kind of example of tall wood buildings. And I mentioned this is kind of a re-emerging trend because there are some much older precedents of multi-story wood structures that are considerably taller than Brock Commons. And a great example of that is the Yingshan Pagoda in Shanxi province, which I think is about 67 meters tall, and for the last 900 years has quite beautifully survived despite multiple severe earthquakes, fires, changing dynasties, and a world war. Its long service life has been attributed to the intricate connection system known as duodong. So you can see here this kind of series of interconnecting brackets on top of the columns kind of lock all the pieces together. So it's not relying on nails or fasteners. It's this really complex detailing of the connections. So this was the world's tallest wood structure for many years until just last year, when the Mjøsa Tower in Norway was completed. And it stands at about 85 meters tall, 18 stories. It's a hotel, private condos, and office building. So it's an all-wood structure, glulam post and beam with heavy cross bracing, and it has a timber facade. So unlike Broad Commons, it doesn't have a concrete core. This is just kind of a schematic of the building itself. So the main structure, glulam post and beams, and then the lower floors use a stress skin panel system, and then the upper floors you can kind of see here. It's actually precast concrete panels. So for taller buildings, they typically govern by wind vibration. So the wind causes the buildings to sway at the top and causes basically motion sickness for occupants. And so the only way to kind of prevent that swaying is to increase the mass of the structure. So the wood was actually too light, so they had to use concrete to on the top to increase the mass and reduce the swaying, so people didn't get sick. Other than that, it's all wood. So you actually have a wood structure supporting concrete in this application, which is pretty cool. You can see some workers here installing the main columns. So those columns are 600 millimeter by 600 millimeter, so 2 foot by 2 foot. So quite large elements coming together. The smaller components were made in a factory, and all the holes for the connections, and the connections were installed off-site, and then nearby the site, kind of all the pieces were put together, and so this is kind of a 4-story frame of all the different components, and they craned it into place from there. It's on the edge of the largest freshwater lake in Norway, so you can see why wind would be a concern, because it's very exposed. And what's really interesting about this is they used a wood facade. So this is like a thermal wood. So they basically take sawn lumber and they heat it up to a high temperature without it combusting, and it basically melts all the resins in the wood, and it makes them completely inert, so that they won't rot or be attacked by insects. And actually it's very hard to ignite, and the flame spread is significantly decreased using that process. So they're able to use wood on the exterior, which is quite unique, because in North America, even 5- and 6-story buildings have to have a non-combustible exterior cladding. You can see the lateral system consisted of these super braces. So you can see these huge super braces that were left exposed and kind of create a unique aesthetic in the rooms. The corner columns were 2 feet by 5 feet, so quite large elements. You can see just nearing completion there. A quick time lapse of the construction process. You can see those frames being installed 4 stories at a time. And the core of the elevator core is all CLT. You have these super braces going up the exterior of the building. Then again, they try and install the closure soon after construction, just to protect it from the elements and prevent driven rain and moisture from damaging the wood structure. And it's not going to structurally damage it. It's just going to create discoloration and a stains. So they want to protect it to avoid that. It's a completed building there. It's pretty impressive. So moving on, this is the last project I'll talk about, and one of my favorites. It's it's in China. It's called the Qingdao Pearl Visitor Center. It's in Qingdao, China, and it was designed by Bolin Zawinski Jackson. So it's an all wood structure, and it serves as kind of a sales center for a new development, housing development, and would later become kind of a clubhouse. So it's an all wood structure and has this really interesting undulating kind of wave roof that was created with NLT panels, and it's all supported on these round glulam columns that were inclined. So I think it's a good example that prefabrication and industrialization doesn't just have to take the shape of kind of rectangular boxes. It can be quite unique structures and kind of free-form shapes. So you can see there the kind of inclined columns creating this kind of network, and the panels themselves had this cable truss system to create a kind of a really long span. So it was quite interesting. So to create this system where no panel was kind of the same, so they just created a simple factory on site. And they just use these simple jigs, and so they set up this 2x8s on edge, nailed together, and so basically each 2x8 is just separated by a fraction of a degree. So you kind of create this really free-form. You're able to create this really free-form shape. You can see the panels being craned into place. They create this kind of really continuous wave shape. You can see this is the factory on site in the lower corner here, and then once completed, they would just be crammed into place. As you see, it's quite a large roof area that was completed this way. But the end result is pretty cool, and it's green roof on the top too, which is pretty neat. That's going to sum up what I was going to talk to you guys about, but I'm always happy to answer any questions, or if something comes up that you think about in the future, you can take my contact info down. I'm always happy to answer questions later.
Thank you very much. It was perfect.
Thank you. Thanks everybody for tuning in and paying attention.
So if you go to the woodsmart.ca website, there are already some publications, and I noticed there are some case studies uploaded in the website.
Yeah, there's some on Woodsmart, and then if you check out cwc.ca too, there's a lot of case studies, different projects.
All right.
Okay.
Yeah, it's a great presentation. Thanks for all the case studies.
No problem. Thank you everybody for paying attention, and yeah, I hope you have a great afternoon and a great weekend.
Thank you very much.